Previous two sessions, we've been discussing this technique that we shall refer to as maximum likelihood, where we're picking the slope parameters. So your beta naught, your beta 1, you always have one more parameter than the number of predictor variables that you're using. Just as in the previous chapter, we start with the simplest case with a single predictor variable. This was balance, credit card balance. So one more than one predictor variable means that we need to estimate these two, your beta naught hat, your beta 1 hat, and they are selected, their values, they're just real numbers. Could be positive, could be negative, could be 0. You then need to check for statistical significance. Although an estimate might not be 0, it might be so close to 0, and closeness is always in the context of the standard error, that you'd actually conclude that there really is no relationship between what you're trying to predict, the response variable, in this case, defaults, does not default, y equals 1 or y equals 0, and the predictor variable that you may be considering or that you may initially have considered for your model. Speaking of standard error, these are the figures for the balance, and you get such a large Z statistic, which give you don't need to know if this is large or small. Forget about that. But what I should have said is the punchline is you get such a small p-value, way less than 1% or even 0.1%, that the usual mantra kicks in, where in unison we all state if p is low, h naught must go. H naught being that beta 1 is in fact 0, the true beta 1 is 0. So if you don't reject h naught, we are rejecting it in this example, but if you don't, you would then kind of conclude that the default does not depend on balance. This is how you make your predictions. Once you've estimated your parameters, then you would imagine, this is what we said yesterday as well, you're the bank manager and you've been asked, or you work in the risk department, and the chief risk officer sends you an email and she tells you, I need to get a good idea over the next 12 months. We expect how many defaults and how large these defaults are. So you take, for example, everyone on the books with a balance of $1,000, and you report back to her and you tell her, well, on the basis of simply their credit balance information, their credit card balance, we think that individuals with roughly $1,000 have a less than 1% chance of defaulting. However, and please do note the non-linearity feature of this model, doubling that balance to 2,000 actually increases the odds by an order of 2. So now we're actually at over 50%, which it's kind of a bit on the risky side, right? And again, that's all relative. There's such a thing as risk appetite. Is it a bank? Is it a lending? Is it a lending institution that is risk seeking? Is it more risk averse? This is part of the governance of any major, banks being, without a doubt, no exception, any major company. What are the risks we're taking? So there's the recognition, there is the quantification, There is the mitigation. So the CRO might tell you, hey, listen, I don't like this exposure. We need to maybe call these clients, tell them, ask them if we can help them perhaps get them better jobs, retrain them, refinance the loan instead of expecting them to pay it off over 5 years. We'll do it over 10 years if necessary. And that's risk mitigation. All these large brokerage firms, Marsh, Aon, they have significant, they play a significant role advising not personal client, not individuals, but you know, these large multinationals, could be factories, you know, large manufacturing plants, you name it. One can use qualitative predictors with the logistic regression model using the dummy variable approach. And we have, as in our data set, we have the qualitative variable student. That is a yes or a no. We can turn it into kind of numerical by saying 1 is if the observation is a student, 0 is if the observation is not a student. And we do that over here. So we're ignoring balance. This is still simple logistic regression. We have a single predictor variable, this time student. When you see brackets, that means that we're assigning the 1 to yes is a student and the 0 to no is not a student. And you get your parameter estimates, which are these two. Place them in your model, which is this logistic expression. And now we're speaking of the estimated probability of default if the individual is a student, and that's 4%, and the probability of default given that the individual is not a student, which is 2.9%. Watch this space, because like we saw later on towards the end of our most recent session, when we use multiple variables for this specific data set in logistic regression, these probabilities are actually in a way going to flip around. We're actually going to see that a student is a safer a student, although it's 4% over here, it's not giving you the whole story, as is often the case with simple, so a single predictor variable. It's not giving us the full story, and once we allow for balance, in fact, students equals yes is actually going to be the safer bet. Multiple logistic regression, same principles, more parameters, since we're not stopping at just x1, but you may have 2 or more predictor variables. One thing the book doesn't do is distinguish between scalars and vectors. So it kind of just expects us to use the context and to guide us in our interpretation of the notation. So this x over here, that's a vector, and this vector describes in the example that we're considering over here, it describes the borrower or the potential borrower. I think what we're going to do very, very soon is we're going to take, for example, their balance and their student status. So that would be a 2-component vector, and P would be 2. Of course, in many ways, you can do away without these dots in that case. So this is your model, and we need to estimate from beta naught until beta P using maximum likelihood regression. I actually found, can I find it again? What was it? It was a Word file, right, yesterday, and I was looking for it during the session. It might be this one. I'll just give you an idea of what's going on in multiple linear regression. What did I just say? I wanted to say in logistic regression. Well, will I give you an idea? Probably not, but this was before we started doing these sessions. I was actually using another book that did have a chapter on not the easiest of texts, which is the primary reason why we're not using this book. But if you're interested, you can look it up. It's Computation Actuarial Science with R, multiple authors. It's one of those textbooks where each chapter is written by a different set of authors who would, you know, their expertise would lie in that content matter. And at some point, I'm sure you're recognizing a lot of the notation, but at some point we could even, it's more of a nice to have, but we can get under the hood of how these betas are actually estimated. But there's a lot of differentiation whenever we see minimize, maximize. That's usually a job for calculus. And you may be familiar, you may be doing this right now. What do you call this at university? Do you have a name for it? This operator? We used to refer to it as nabla. It's also del. Anyway, we use just multivariable calculus, right? I had also done something in Excel. If I find this file, we could even play a bit with it. Okay, again, I'm speeding through these first few minutes since this is all material relating to yesterday's session.
Sir,
Yes, please.
can you go back to the Word document?
Yes. I mean, I shouldn't even be showing you this because there's a lot of notation. I'm not expecting anyone to make heads or tails of it. Did something in particular strike you? You're muted right now. I don't know if you have a question or you lost connection. Okay, so or did I get disconnected? Can anyone else hear me? If you could just maybe confirm. We were saying, hope it doesn't happen again.
Do we need to be able to understand this notation for the upcoming actuarial exam?
That's a good question. This would be CS1. So this is what your colleagues are doing in April, whereas I think in your case it probably makes more sense to do CM1 in September. But this is all A-level, isn't it? Seeing it like this, now this is very responsible of me even to show you any of this. But I'm sharing it for two reasons. Number one, just so I don't forget that I actually have this document, and at some point, although the book doesn't go into it, it would be great to maybe develop a more mathematical, rigorous understanding of what we're going to do towards the end of this chapter in RStudio when estimating the betas. But is there any notation that you're not familiar with? In fact, if you had to, I don't know if there was something in particular that maybe caught your attention.
Where there is differentiating log
This
L of beta. Yes, there would I forgot what it's called.
nabla.
No. You have the numerator in the
Partial by partial.
Yes, all right, partial.
Yes, but you're doing that, I think, aren't you, elsewhere?
Yes, in the beginning.
Yes, yeah, yes, it's not that difficult, in fact. I would say. And obviously, it's easy when when you've been doing things for a number of years. Don't let the notation put you off. And we've already seen partial derivatives in chapter 3. At least the notation, we have seen it. Now, what's interesting is that you actually get a negative parameter for student equals yes. And this is what we discussed yesterday, that although overall, and I do encourage you to go back to yesterday's session if you'd like an in-depth explanation of all this. But just very quickly, although when you're only looking at student as a predictor variable, you will get students default. Students are orange. Students default. This is default rate. So they don't pay their loans or they miss out on loan payments, excuse me. That students default at higher rates than non-students, but that's overall. In fact, for a given balance, it's typically the case, in this situation, it's actually always the case, that if you know the balance, so for example, 1,500, it's more likely that the non-student defaults than the student. And this is why we get negative. Actually, if you are a student, you are a safer bet. Once we allow for balance and income. Like I said, we're just going over things very quickly over here. And then we took a specific example. I think this was the very last thing we did. A student with a credit card balance of, without plugging in the numbers, once you've built the model, and building the model, it's really, we're keeping things very simple for the time being, but I would describe the 3 major steps that we're considering. Collecting the data, and the data was in the ISLR package, which we've been looking at these past few sessions in R. Picking the model, and we picked a logistic model. And once you've picked the model, you fit the data to the model. No, you fit the model to the data, of course. And with these parameter estimates, there is quite a bit of lightning over here. So if I do get disconnected, you could always message me on our group chat as well. If I don't notice that I've actually been kicked out and I'm just speaking to myself. And we plug in the 3 characteristics. So let's say we have a student, so 1, not 0, credit balance of 1,500, and we're measuring in thousands over here. That's just how we've parameterized the model. So the estimated probability of default given this 3-component vector 1,500, 40, 1 is 5.8%. On the other hand, if it's a non-student, that probability doesn't quite double, but it does go from 5 to 10%. Logistic regression for more than 2 response classes. So up to this point, we've been working with a binary response variable. It may only take 1 of 2 possible, let's call them values, or classes, right? To borrow the word from the heading. Default yes, default no. We sometimes wish to classify a response variable that has more than 2 classes. For example, in section 4.2, we had 3 categories of medical condition. in the emergency room, stroke, drug overdose, epileptic seizure. In this setting, we wish to model both probability y equals stroke given x and probability y equals drug overdose given x. X would be the symptoms, right? I think we had discussed at the very beginning of this chapter. With the remaining probability y equals seizure given x. Right, so you can ignore one of them because if you know 2 out of 3, the third probability is simply 1 minus the 2 other probabilities. The two-class logistic regression models. Okay, so that's hyphenated, right? So I'll do a better job of reading it. The two-class logistic regression models discussed in the previous sections have multiple class extensions, but in practice, they tend not to be used all that often. So sometimes it's just a case of what some people call the customs of the tribe. If practitioners aren't really using certain models, you yourself may be less inclined to use them. One of the reasons is that the method we discuss in the next section, discriminant analysis, is popular for multiple class classification. So we do not go into the details of multiple class logistic regression here, but simply note that such an approach is possible and that software for it is available in R. When we say software, probably a specific library. That's one of the key reasons why R is so popular. You get to download all these tried and tested, free of charge, I think all of them to my knowledge, libraries. Linear discriminant analysis. Logistic regression involves directly modeling the probability that the response is k, given that the vector x has these p components, using the logistic function given by 4.7 for the case of two response classes. In statistical jargon, we model the conditional distribution of the response y, given, and this is what we mean by that line, given the predictors x. We now consider an alternative and less direct approach to estimating these probabilities. In this alternative approach, we model the distribution of the predictors x separately in each of the response classes, i.e. given y, and then use Bayes' theorem. We'll have to see in what detail this book goes into Bayes' theorem to flip these around into estimates for probability y equals k given x. So what are we flipping? We'll first look at the distribution of x given y. Then we'll use Bayes' theorem to flip them around and get what we were calculating directly, or the same thing that is calculated directly in logistic regression. When these distributions are assumed to be normal, it turns out that the model is very similar in form to logistic regression. Why do we need another method when we have logistic regression? There are several reasons. When the classes are well separated, the parameter estimates for the logistic regression model are surprisingly unstable. This is what you don't want in your model, that if you change your data slightly, the parameters are considerably different to maybe a previous model fit. Linear discriminant analysis does not suffer from this problem. If n is small, n is the number of observations, correct? And the distribution of the predictors x is approximately normal in each of the classes, the linear discriminant model is again more stable than the logistic regression model. As mentioned in section 4.3.5, linear discriminant analysis is popular when we have more than 2 response classes. Yeah, so it's not a mathematical reason, but it just kind of like the traditions of the trade. Now, I'm hoping that this book gives us a nice introduction to Bayes' theorem, because while you are going to have as many actuarial exams as I had on Bayes' theorem, don't ask me to write the formulae. But I do have a good understanding of how the theorem works, so let's have a look. Suppose that we wish to classify an observation into one of k classes, where k is greater than or equal to 2. In other words, the qualitative response variable y can take on k possible, distinct, and unordered values. Let pi k, and as soon as the mathematics start, this is where we slow down, right? Let pi k represent the overall or prior probability that a randomly chosen observation comes from the kth class. So we have this word, prior. There are many ways of thinking of prior. Very often it's kind of like your prior beliefs. So for example, is there a teapot orbiting the Earth? Or for example, will the sun rise tomorrow? A lot of what we, when it comes to modeling just our day-to-day experiences, there is, many would argue, a large component to that is what your prior beliefs are. Now one would hope that you're regularly updating your prior beliefs. But you tend to start with some kind of rough idea. It could be a good, statistically sound belief of what the likelihood is, but you would have a prior belief, and this is what pi k is. Pi k represents the overall or prior probability that a randomly chosen observation comes from the kth class. I haven't quite understood this yet, but so let's see. This is the probability that a given observation is associated. So for example, I give an observation a patient at the emergency room is associated with the kth category of the response variable. So think of this as we're one of the nurses at the emergency room, and we have, as soon as we see the patient, even if maybe we haven't looked at all their symptoms yet, or any of them, but maybe without even looking at the patient at all. Maybe we know that Friday nights, 80% of patients that come to the emergency room, it's maybe drug related or alcohol related. Just giving an example. So that's your prior belief, maybe even without looking at the patient. So you say, okay, today's a Friday, and one of these Ks, one of these, where's my one of these classes is drug related, and you say, okay, then pi drug related is 0.8. Now, so that's all this in the pink. Pi k is the prior. The prior what? The prior probability that a randomly chosen observation from our data set has as a y class k, lowercase k. Okay, so that's the first step. That's your prior belief. Let f subscript k of x represent the probability, let's use a different color, the probability that x is x given y equals k. Denote the density function of x for an observation that comes from the kth class. What are we saying here? So I think pi k is relatively straightforward. Pi k is pick a random observation and it's your prior probability that that observation has a specific class. Seizure, stroke. Now what is this? What is this? This is the probability that that x has these characteristics. Remember, very often it's going to be a vector given y equals k. So can we come up with an example? So you could say, for example, the probability that, let's say we're just looking at one symptom, that x is equal to, what kind of symptom can we take? Can we take an easy one? No, coughing. Given y equals seizure. And we're going to refer to this as the density function of x for an observation that comes from the kth class. In other words, fk of x is relatively large if there is a high probability that an observation in the kth class has x roughly equal to x. Yeah, okay, I think I'm understanding it. It's strange that they've used the lowercase, but what they're saying is, If there is a high probability that an observation in the kth class if there's a high probability that an observation in the kth class just going to mute my mic for a second. I'll soon be. I'm sure things are going to be easier with an example, but if there's a high probability that an observation in the kth class has x roughly equal to x, and fk of x is small, it is very unlikely that an observation in the kth class has x roughly equal to x. It's probably not too difficult, but it's a bit abstract right now. We're just saying all these x's and y's. Fk of x is relatively large if there's a high probability that a patient in the seizure class has these characteristics. I think there's a typo. I think there's a typo. And the typo is this should be lowercase. This should be lowercase, which is why they have identity. They're saying for every value, every lowercase x. Not necessarily. These books are usually, it's not just notes. They would have proofreaders, but this has to be probably lowercase. And what we're saying is different probabilities. Let me just do my best. But then they say density function of x, and they use the density function of x for an observation that comes from the kth class. Let's read on. We'll definitely figure it out. And then we speak of Bayes' theorem. Now Bayes' theorem is where you get to swap them around. Let's see. And how are we doing for time? Yeah, so we have easily 20 minutes if you're up for them. Let's have a look. So now this is just Bayes' theorem. There's nothing to understand over here. We're not going to do the proof or anything. But Bayes' theorem tells us this. If you want to know, might type it into Word, might make more sense of it this way. So what's Bayes' theorem telling us? We're saying the probability. I'm using very small text. Let me just change the font. The probability that this, okay, and just think of a specific example. probability that Y is seizure. And hey, let us say X is the age. Let us keep it a single predictor variable. So age is 40. We'll call it a symptom, right? I mean, it's a patient characteristic. Let me call it the age random variable is equal to, let's see. We'll unpack everything as necessary. Let's just type it for the time being. Do not be afraid, or be not afraid. Sometimes you need to just be a bit stubborn as well. You just need to keep on, although taking a break and coming back to it the next day does work miracles. But that's being stubborn, right? Not giving up. But just because you walk away from something with the intention of coming back to it at a later stage, that's maybe a healthy or well-balanced type of intellectual. Stubbornness has maybe negative connotations, but resilience, stamina. So let's see. Like this, we're hardly going to understand much. What was this? This represents the probability, and I'll just copy it from the book if necessary. The probability x is equal to k given, excuse me, x is equal to x given that y is equal to k. That's what we're saying, right? The notation is just to simplify things. The probability that x is equal to x given y is equal to k. It's a very easy result. Don't be discouraged. We're not quite making sense of it yet, but we'll get there. We shall get there. Whereas this is equal to L, right? That is equal to L because it's FL of K. Now, L is just a dummy variable, it doesn't mean anything, but it runs through all the classes. So the first class, second class, etc., etc. So what we're saying over here is your prior estimate of probability seizure times, primary school multiplication between two real numbers, age 40 and y equals seizure, divided by, let's say that we only have two classes so that everything fits in. Let k equals 2.
Sir,
Yes, please.
do we know the sample size or no?
Does it come into play at this point? When you say sample size, which data set were you referring to? The sort of the patient data?
But how am what's going through my head right now is that we're calculating the probability of a 40-year-old person having a seizure from a sample of people, but I don't think that's the case, honestly.
So you're referring to this, right? You're referring to
To the
probability.
left-hand side.
You're referring to the right, I think. You said the probability of a 40-year-old.
Yes.
Yeah, you're referring to the probability. this is let's just make sure that we're comfortable with these probabilities. So you said left hand side. So this is the probability that if the patient had a seizure, then their age at the time was 40. This over
Ah, all
here,
right. I think it was that vertical line that confused me a little.
whereas this over here is no, I mean I think it's practically what you were saying. Now whether it was left or right, this is the probability that a 40-year-old probability that of probability that if the patient no the probability that a 40-year-old patient was admitted with a seizure. So this is what is the probability of having being admitted with a seizure if you're 40, and what's the probability of being admitted at age 40 if you had a seizure? Now, yeah, how are we going to get these probabilities? And this is why maybe you're asking about sample size. We'll have to continue reading on. Just very quickly, let's say that let k equals 1 and the classes are seizure and whatever, right? What were they in the book? You can tell, yeah. So overdose. I'll just type drug. I'll type OD. Yeah, whatever. Drugs. Drug overdose. Drug overdose. So now what we get is these are our two L's. L1 for seizure, L equals 1 seizure, and L equals 2. So what do we get? We get all this for seizure, but again for okay, that's not good. Let me but no, I changed seizure to drug overdose. So this is Bayes' theorem. If you want to know the probability, that a patient is admitted with seizure given an age of 40, then you flip the conditionals around and you get this over here. Now exactly which direction we're going to take this, we have yet to see. Let's see. In accordance with our earlier notation, we will use the abbreviation pk of x for this. Yeah, it's what we were doing for default, right? So going back to the book. Whenever we had anything like this was probability default given x. But now that we have multiple classes, how can we? But now we'll use a subscript. So earlier we weren't using a subscript because it was just two. It was just two classes. Yes or no, default yes, default no, and we're just taking sort of. We're just assuming. No, not assuming. That's the wrong word. Since it was two classes, and if you know the probability of one, then you automatically know the probability of the other. By convention, we just said, okay, let this be probability default, and then you just subtract 1 to get probability does not default, because there were only 2 classes. But now, since we may have 3 or more classes, we use a little subscript. So all this shall be abbreviated to P subscript K of X. Meaning in this case, how do we abbreviate this? We would say the probability seizure given that the age is 40. So you just say 40 like that, okay? This suggests that instead of directly computing the probability that y is k given x, as in section 4.3.1, so this is the logistic model. We can simply plug in estimates of pi k and fk of x into 4.10. In general, estimating pi k is easy. We have a random sample of y's from the population. We simply compute the fraction of the training observations that belong to the kth class. However, oh, by the way, the sum of pi's should add up to a 1, right? I think these pi's would add up to 1. So for example, probability seizure, this would be 80%, this would be 20. So that if you're only allowing for the possibility of having 2 of them, and there's nothing else out there. However, estimating fk of x tends to be more challenging unless we assume some simple forms for these densities. So apparently this is going to be the challenging part, the fk. If we highlight it, this is going to be the challenge. The challenge is estimating these two. The probability that if you are age 40, then you're going to be in the emergency room with a seizure. It's a density. When we say density, if we can go back, it's a density because, of course, we'd also like to know the age, the probability when the age is 39, you know, for every conceivable age. Remember that is our input after all. So it's actually quite important. So you are asking what is the probability of seizure given a certain age? With Bayes' theorem, we may answer that question, but you first need to know the probabilities flipped around. What is the probability of that age given seizure? Remember, the question is trying to classify So what we're doing in this, I don't even know the name of the model, linear discriminant analysis. The way linear discriminant analysis works is, given a characteristic, it could be a single aspect, one predictor variable, it could be multiple predictor variables, given the information you know, then you would like to given the information you know on a specific observation, on a specific data subject, you would then wish to classify that data subject. Now, we're going to rely on Bayes' theorem, but to do that, we need to know probabilities like these two: the probability that age is this given seizure, the probability age this given drug overdose. We refer to pk of x as the posterior probability that an observation x equals k belongs to the kth class. That is, it is a probability that the observation belongs to the kth class given the predictor variable for that observation. We know from chapter 2 that the Bayes classifier, which classifies an observation to the class for which pk of k is largest, has the lowest possible error rate out of all the classifiers. I don't even remember doing this. This is, of course, only true if the terms in 4.10 are all correctly specified. Therefore, if we can find a way to estimate fk of x, then we can develop a classifier that approximates the Bayes classifier. Such an approach is the topic of the following sections, and it looks like a good place to stop, but it's going to get quite mathematical. Looks like fun. Yeah. Yeah, I'm really excited to do these next pages. We'll definitely, when we resume, we'll definitely go over all this again. And as always, a word of encouragement: when we come around to looking at the second time, we're definitely going to make more progress than today. I'm just going to stop the recording.